Welcome everybody. Thanks for coming. Well, to be clear up front, this is a non-mainstream approach. I don't think most of contemporary theoretical physics makes sense. I don't think the standard model makes much sense, mostly because it's much too complicated, and as King Alfonso a couple of 100 years ago said, if the Lord Almighty had asked me before embarking creation, I should have recommended something simpler. So basically, as I have argued in other places, I think we have to go back to 1930, maybe to the philosophical approach of the physicists back then. I just would like to remind that people like Einstein have repeatedly said, I cannot imagine a reasonable theory containing arbitrary numbers, and today we have hundreds and dozens of numbers in the standard model. So this is an alternative approach, and it's about fundamental physics. The questions which are arising are, why does the peculiar structure of electrodynamics exist at all? And this is closely related to the question, why is space-time 3 + 1 dimensional? And are there mathematical structures that can represent this, that can explain this from first principles? Okay? So, and if you look at the history of mathematics, there is a very interesting development. In 1843, the famous Irish mathematician William Hamilton discovered a four-dimensional algebra. The question was, can we define a reasonable multiplication in 3 dimensions as it was defined in 2 dimensions by complex numbers? And the answer was no, you need 4 dimensions. And he had this beautiful insight in 1843 that in which he invented these quaternions, and I'm considering today the unit quaternions. That means a 3-dimensional manifold that would be the equivalent to unit complex numbers, which are 1-dimensional, while complex numbers as such as 2-dimensional. So we are considering a 3-dimensional manifold. And why is this interesting? Because it shows up in several contexts. You may look at it as the unit 3 sphere, also as the rotations in 2 complex dimensions. It has a meaning as the double cover of the usual rotations in 3-dimensional space, as we will show. And this is more for mathematicians. The Hopf vibration is a very interesting feature, and it's the Poincaré conjecture was proved by Perelman, who said that S3 is the only simple connected 3-dimensional manifold, and it is, so to speak, the half of SO4, which is 6-dimensional. This is interesting. The methods, just to mention here, this is a very brief talk. Cannot do much derivations or even proofs, and this theory is not in an appropriate state yet. I will try to visualize unit quaternion multiplication and show that it has a similar structure that reminds us from electrodynamics. All this is an intuitive approach and just a first idea, of course. So what does stereographic projection mean? Everyone is familiar with stereographic projection in 2 dimensions. 1/2 of this sphere is projected to the inner of the unit circle, and the other half is projected to the outer of the unit circle. And in an analogous manner, this works in 3 dimensions. So we can project these S3, the 3-dimensional unit sphere, to ordinary Euclidean space in 3 dimensions. And I shall make use of the videos of Ben Eater. It's a wonderful website with clickable videos, and you can produce your own animations. That's a very nice site. I heartily recommend. And I tried to play my videos here. I hope these will be visible more or less? Maybe you can give me feedback. We are just visualizing two-dimensional stereographic projection here. Okay. And now we're going to, I should stop here, and I go to 3 dimensions. The usual, we have 3 complex dimensions here, I, J, and K, and these are the complex units are projected to the usual X, Y, and Z units in the Cartesian space, while the 1 is projected to the origin in this projection. And again, a little visualization here. You can move around, and now you can insert circles. One of the circles in which there's the real dimension appears as a straight line, whereas other circles in the complex dimensions are real circles, and then you have spheres, and you can visualize these stereographic projections and S3 in a very nice manner here. I go ahead, and here we have the next animation. Yeah. Again. Okay. So now it gets really interesting, and what I'm doing here is applying left and right multiplications. I should add that it's not commutative anymore. Left multiplication does something else than the right multiplication, but we can visualize this very beautifully. I show you the first video with a left multiplication, and you see here in top left the corresponding unit quaternion. I start from the unit quaternion, and now if I do a multiplication in I direction, you see I'm pushing the green line towards the left, and now I'm pulling it, and the circle rotates in anti-clockwise manner, and vice versa. I'm pushing again the green line, the circle is rotating in clockwise direction. So what we have here is a screw sense, and look at the difference now. If I do the same multiplication with the same number, but from the right side, I push the green line, but at the same time the circle is rotating counterclockwise, and if I'm pulling with my multiplication these 2 dimensions, the circle rotates the other way. What we observe here is a screw sense, and if I had my camera, I would just bring a towel here, and what you can do with a towel, you wring it out the water either with applying a right-handed torque or a left-handed torque. So we have something very fundamental occurring here. What I mean is, just by mathematically pondering over the question, is there a reasonable multiplication, we end up with a qualitative property similar to complex numbers. I remind you that complex numbers are multiplications in 2 dimensions, but what naturally occurs here is a rotation. Okay, so unit complex numbers do rotate the R3, but unit quaternions do much more with the regular 3-dimensional space. They apply something like a screw sense or a helicity to the entire manifold. And this is, I think, a very exciting observation, because screw sense and helicity is exactly what we observe in elementary particle physics. We have positrons and electrons, and these particles have proven to have a helicity. There was the Nobel Prize in 1957. Actually, the discovery, the experiment was done by this lady, and the 2 guys got the Nobel Prize. That's sometimes how the Berkshire works in physics. And yeah, but this is, well, very interesting because it could mean that left-hand and or right-hand multiplication is somehow related to electric charge. And now we are considering general multiplications. And first of all, I show that by applying left-hand and right-hand multiplication with the conjugate, the complex conjugate, I can generate pure rotations. Okay, you note here that I multiply from the right-hand side with the complex conjugate. It's not an arbitrary number, but I can do any rotation with this system. Okay, so we are still in a three-dimensional manifold, so to speak, because once the number is fixed, the complex conjugate is fixed. And but the general multiplication, I should go to the next slide, but the video restarts, sorry. So, well, this is of course well known, rotation formulas in 3 dimensions. There are even computer applications to do very conveniently 3-dimensional rotations with the help of unit quaternions. But if we go now to the general multiplication, we have a 6-dimensional manifold. And again, the first seconds are about pure rotation. You see still the conjugate complex, so these are all rigid rotation, but now I take away the constraint and I have a general multiplication from the left and from the right. That means I have 6 free parameters, and I can beautifully visualize with this tool a 6-dimensional manifold, because I have 3 dimensions applied from the left and 3 from the right. So let's add a sphere just to show some nice pictures. Look at how this sphere transforms. Sometimes transforms into a plane. If I do a multiplication for 2 pi. And okay, as I said, all this can be very nicely visualized, but the interesting thing is here that actually doing right and left multiplications with these unit quaternions corresponds, I have difficulties, yeah, okay, we're here at the next slide, corresponds to the isoclinic decomposition of the unit rotations in 4 dimensions. And this of course is this of course already reminds us from electrodynamics, because we have 6 dimensions of electric fields and magnetic fields. But I shall give another little example before how to realize pure shifts. Pure rotations I can realize with the multiplication of the complex conjugate. But if I multiply with the same number you see here, I realize the pure shift by compensating for the rotation. And so the guess would be that maybe electric fields can be related to pure rotations, and magnetic fields could be related to these shifts. We have 6 dimensions in both cases. And well, I shall add another. This is of course very intuitive and may seem very vague, but if you think about first principles and how to explain the very structure and the very origin of electrodynamics, I think it's a nice idea. And it's also related to the ether theories in electrodynamics, in particular to McCulloch's incompressible ether in 1839. And I'm not going into details here. This would be the relevant paper. There are, of course, many problems and a couple of questions which would arise. How can I imagine adding vectors, which would be the conventional formulation of electrodynamics, adding vectors, but here we have a different thing. You have just multiplications, and this could insert some non-linearity. We would have to pass to multiplying quaternions. Then instead of derivatives, we would have to consider Lie algebras, because S3 is a Lie group, or the unit quaternions. So of course there are more questions than answers. Left and right multiplication, could these multiplications be related to charge? Is SO4 related to the electromagnetic field? Probably, with electric field as pure rotation and magnetic field the pure shift. How would you define differential operators properly? Can quaternion multiplication of elements close to unity look like vector addition? What happens if you just have group multiplication but no addition? All these, of course, are unsolved questions, but all this is part of a more general approach. As I said, we need to go back to 1930. Maybe not everyone agrees, but in 1930 we had the kind of peak intelligence of physics, of simplicity. We had the minimal number of physical constants, and if we question the very origin of these remaining physical constants, why does C exist after all? Why does Planck's constant exist after all? There are no a priori reasons, and I have argued in another place that in order to explain the very existence, we have to put into question the very concept of space and time, because there is no explanation from first principles that space-time presents itself in such a peculiar manner. We should have a mathematical explanation for the very different phenomenology of space and time, and because these are concepts most easily accessible to human perception, but then space and time may be inappropriate to when describing physics on a fundamental level. So this is these ideas about electrodynamics are a spin-off of these more general considerations about mathematical reality, space-time, and fundamental constants. I have still a little. Do I have time anymore? Well, unfortunately, I think I'm running time. No, I'm finishing soon. Can you should probably wrap up, because I would like. I will speed up. Okay, a lot of unsolved questions. Alternatives to reality. Just a link to other talks I have given at the mathematics conferences to this. This is related to problems of current physics, and this is a paper about constants and simplicity underlying the argument of natural constants. And this is a related older article in Annalen der Physik, and this is a book about the mathematical reality. And okay, so I will stop here and be happy for any questions.
Yes,
thank you
so far.
Very
much for the thanks for the beautiful talks. Or other questions? I mean, I have some questions, if I may, just for clarification for myself. I mean, can you explain? I mean, I understood that essentially you are rewriting Maxwell's theory of electromagnetism in terms of quaternionic variables, because you can consider the E and B field as some representations of SO4 and so on, and this is certainly something which is sensible to do, but I don't see how this adds any new physics to Maxwell's theory. So my question is, where do the can you address this comment, and can you explain where these natural constants and this added simplicity come in your approach?
Okay, so it's basically your question is twofold. Well, first, Maxwell itself did write his electrodynamics in a quaternion form, which is not known very well. However, your question, what does it change? Of course, it's something very profound that would change, because if electric and magnetic fields are not properly described by vectors, so to speak, you have to forget about all the vector analysis and describe it with different mathematics, which are multiplications of quaternions. So you would insert non-linearities, some tiny effects that would indeed also lead to new predictions, because the superposition principle would be violated in this case in a very tiny way. And the second question, how this relates to physical contacts, well, that's a large that's a large area to cover. As I said, if you go to fundamental physics and take the perspective that you need to explain fundamental constants, modern physics does not care about this, let's say. But the people around 1920, they had the impression, and they were convinced that you have to explain all these numbers, and if you bring these thoughts to the end, you end up with this kind of question, so to speak. Yeah.
Yes, okay, I understand. And there's another question, so maybe we should move.
Yes.
Thomas, please.
Yeah, just one brief question. So, are you aware of that there is a nice book by Adler on quaternionic quantum mechanics and quantum fields? So, if you allow me to share the screen, then I can...
Adler? Okay, I can do that. Yeah, I stop here. But I have noted it. Adler. Yeah, I mean...
So that's the book.
I mean, quaternions are a very interesting thing, because they contain, so to speak, both the electric fields, the mathematics of electromagnetic fields, and also they are also related. They contain complex numbers, so you can relate them to quantum mechanics. So there are a variety of approaches, so to speak, how to do fundamental physics. They're not necessarily in line.
For instance, all the spin 1/2 physics is simply done in half-integer representations of the rotation group, which is equivalent to quaternions.
Yeah, I'm not sure I'm in line with all this, but this was one of my main arguments, saying that we have to give a first principles explanation of spin. Okay, what is this? I mean, spin arises very naturally if you just realize that S3, the unit quaternions, are a double cover of the usual three-dimensional rotations.
It's this usual Dirac type of theory we are all aware of.
I'm not sure you're all aware of, but if you're interested, so I hope this will be fruitful. Okay.
Okay, yeah. I think it's good to have a lot of discussion, but I think in view of the time we should probably move on. So thank you very much again for your very nice presentation. Thanks a lot.
Okay, thank you everybody, and goodbye.